For this next lecture, we're going to talk about physics, just in review, a bit about instrumentation and the workings, knobs of the machine, and then some artifacts here at the end. So we have to review some physics and then just understand how the machine works in order to really interpret the image properly. So what happens is that you have an electrical current that goes through the wire here of the machine to the transducer, and at the tip of the transducer there's these small piezoelectric crystals. There's literally crystals at the end of this transducer, and what happens is the electrical current vibrates those crystals and they shoot a pressure longitudinal mechanical ultrasound wave into the patient. So that wave shoots on down, it hits something along the way, whether that's tissue or bone or air or whatever. Some of those waves get bounced back to the transducer, and then the machine interprets that and just puts that up on the screen, and then it's your job as a clinician to interpret what you're seeing as well. As the waves go down into the body, they get attenuated, meaning they lose their amplitude, the quality of the signal goes down, and then a bunch of other things happen too, like artifacts, scatter, absorption, refraction, things like that. So amplitude goes down as the sound wave gets attenuated through the body. Amplitude equals intensity, so the intensity of the wave decreases as you go deeper in tissue. And remember that the attenuation is proportional to the frequency of the wave. So the higher the frequency of the ultrasound wave that you're using, that's often on the transducer itself, the more attenuation you're going to have. But also note that the higher frequency also gives you the better resolution image, but those are always going to be superficial images. So here's a little picture of the transducer on the top here. It shows you how the crystals are sort of marched out in line at the end of the transducer, and those are again vibrated with an electrical current and send a mechanical wave through the patient. And it's worthwhile to note that the transducer functions in a pulsatile way where it sends a signal out for about 1 millisecond, and then it listens, or it kind of absorbs those sound waves back in order to put them up on the image for you for another 9 milliseconds. So only shooting out waves for about 10% of the time. The vast majority of the time it's listening or kind of recording those sound waves coming back to it. And how it judges the distance of the tissue that you're trying to image, it's all based on the velocity, the speed at which the sound bounces off that tissue and then returns to the transducer. So it's recording those times, recording how long it takes for the sound waves to bounce back, and that's how you get tissues at distinct depths within your image. And then in addition to the time it takes for the sound waves to come back, how intense or how high the amplitude is of those waves returning to the transducer gives the machine additional information about what kind of signal it's getting back. So the more it gets back, the brighter basically the image will be. And then you can interpret that as understanding how dense the tissue is and what kind of tissue you're looking at. Now to quickly review the frequency, like we said before, so the frequency is measured in hertz, which is cycles over seconds. So the more cycles you have in a given time, the higher the frequency is. Higher frequency in ultrasound is really good for high resolution images, but it doesn't penetrate well because you have high attenuation. And then the opposite is true for low frequency. If it's a low frequency transducer, you're getting this resolution that's not quite as good, but you can penetrate further into tissue because you have less attenuation. Here's an example on the top of a high frequency image. And so that's the eyeball. And so I don't have a lot of depth here, just 4 centimeters, but really good resolution. Whereas on the bottom image, there's the heart with the pericardial fusion and the liver. Very good depth, but the resolution is not quite as good. So let's talk about probe selection now that we understand about frequency. That'll really help us decide what kind of probe we're going to use. In addition, the shape of the probe might make a difference when you're choosing it, because you might need to image a certain area that's either big or small, or fit between the ribs, or one that's made for motion or not motion. So here's some of the main transducers we use. One is the curvilinear convex array probe, and this is a low frequency probe, so 2 to 6 megahertz, and it's often referred to as the abdominal probe because, again, it's low frequency, good penetration, but pretty poor resolution. It gives you a nice sort of global view, nice big footprint of the patient's tissue. The phased array probe, or the cardiac probe, is also a pretty low frequency probe, 1 to 5 megahertz, really designed to see motion well. And also it's a little bit different, where the sound waves just originate from the very middle of the probe, which makes it really good at shooting in between ribs, and one of the reasons we like to use it for cardiac imaging. Now, these linear probes are almost always high frequency probes, so they're going to start around 5 megahertz and they're going to get up to 15 or sometimes even higher now. And so they're really designed for superficial structures and really good resolution. So you're using these for procedures, vascular studies, eyes, soft tissue stuff, MSK, things like that. Now, a concept that's really important is that the time that the echoes return to the transducer equals the distance that the machine's going to interpret on the screen here. So there's 3 options basically when you shoot ultrasound into a person. The pulse wave is going to enter and it'll get reflected back, and then you'll see hyperechoic or echogenic material. And when you see that, you're going to interpret it as bone, stones, or metal, something that is very dense and something that reflects almost all the sound waves. The next possibility is that the pulse wave or the ultrasound goes into the patient and there's no reflection at all. The waves just go right through the tissue. If that happens, then things are going to look black because there's no echoes. So that's known as anechoic, or no echoes. And that happens with fluid, or that happens behind something that's very hyperechoic, so a shadow would look black. But urine, blood, aqueous humor of the eye, that's all going to look anechoic because the sound waves travel right through water. They don't bounce off anything. So kind of the opposite of our first scenario where all the waves are bouncing back. And then the last option, when you shoot the ultrasound through tissue, some's reflected and some's not. And that's everything in between this hyperechoic, very hyperechoic, and anechoic structures. That's going to be things like liver, muscles, all the other organs, where they're going to be hypoechoic or hyperechoic relative to each other, but they're not going to be this very bright white or black structures. So echogenicity, and that's the term we use when we're talking about ultrasound, is relative to the surrounding structure. So in this image, the circle in the middle of that picture is hyperechoic compared to all the stuff outside of it. And so if we're talking about that structure, we'd say that's hyperechoic. If we're talking about everything else, it's hypoechoic related to that circle. As compared to this one, that circle in the middle is hypoechoic relative to everything outside. And then the last scenario, that circle in the middle is anechoic, or has no echoes. When we're talking about ultrasound, we talk about planes of the body because we have to orient ourselves, especially when we're describing images to other people. And when we review these images later, we want to kind of have an idea of what axes of the body we're using. So it's a good idea to memorize the axes of the body, the coronal plane, sagittal plane, axial plane, so that when we describe ultrasound images, we all have used the same nomenclature. And axes can also be related to the organ you're studying. So you might describe a long view of the kidney versus a axial view of the kidney, and that's just related to how the organ is sitting in space. Here's an example of an ultrasound done in a long axis of an arm, and then a transverse or axial axis of the arm. It kind of shows you how that ultrasound projects right out of the transducer, and when it's going up and down along the long axis of the arm, we call it longitudinal. And then when we're cutting the arm sort of in half or in a short axis, we call it transverse axial or short axis. Let's talk a little bit about the knobs of the machine, just a few basic ones that you want to know about. So you might be exposed to the Zanari machines that we have in our department, but there's many other machines, and we'll show you the Sonosite as well. So gain is the first one to be aware of. Gain is really the brightness of the image, and you can turn that up or down. And often you have near gain, far gain, and then overall gain. And what that means is that the near gain is sort of at the top of the image, the far gain is at the bottom, and you can individualize those because sometimes things can be brighter on top or brighter on the bottom, and you want to change that. And then the bottom knob is the overall gain. And so this image here, we would describe this as sort of undergained, where there's not a lot of brightness to this image. It might benefit from a little bit more gain. Compared to this one, where the image is very bright, it's probably overgained, where it's so bright it's actually hard to distinguish between tissue. And this image is more ideal, where we're using the proper amount of gain. So we kind of had too little and too much, and then this is just right. Let's talk about the depth. Depth is important. You only want to use the right amount of depth, because too much depth, and here's an example of this image on the right where we're kind of looking at the gallbladder, which is right in the middle. We could have reduced our depth by quite a bit. Remember attenuation? Attenuation is when the amplitude decreases as the ultrasound waves go deep into the tissue. And so your image quality, or the intensity of your image, decreases as you go deeper. Therefore, you only want to go as deep as you need to when looking at your image of interest. So for it's this gallbladder, we could decrease our depth and had a much tighter image. So go up and down the depth until you get kind of what you want. And here we switch the depth, and now our gallbladder is much closer to the screen. We can see it in better detail. There's a little bit of depth left underneath it, but not too much, not too little. That's kind of what we want to see here. I'm going to talk real briefly now about a couple artifacts. There are many others, which we'll cover in another lecture. But artifacts are something that are artifactual on the screen. They don't actually exist. They're just a factor of the acoustic properties in the tissue that are being imaged. We talked a lot about attenuation. So remember, attenuation is when you have progressive weakening of your ultrasound beam. It's related to frequency, so the higher the frequency, the more attenuation. And as the ultrasound beam goes into the tissue, it just naturally gets attenuated the deeper you go. Reflection is what we want to happen. That's when the ultrasound waves bounce against the structure and come back to the transducer, allowing us to interpret it. So we like when that happens, but when that happens too much, that can be very bright, and that can cause shadowing, things like that. Scattering occurs often with air. It's when the ultrasound waves hit something, they get scattered all over the place, and most of those waves don't make it back to the transducer, although some might. And that can give you this sort of dirty shadow, as we describe it, appearance. Refraction happens when you have two tissues next to each other, especially if that tissue is very thin and dense and fibrous, such as the diaphragm, and that can make those waves, ultrasound waves, really refract and curve around that structure. And absorption. Absorption always happens, and it's just part of the process of using a wave, because a mechanical wave, it is energy, so some of that will be converted into heat. And that's one of the reasons we want to kind of reduce our power of the ultrasound wave to levels that are not dangerous, to levels that are not going to create too much heat. So one type of artifact is a high attenuation artifact. That's when sound encounters a high attenuated surface. The echoes are diminished posteriorly, and acoustic shadow results. So examples of this would be a gallstone or bone, or perhaps something metallic. So something that bounces all those, or reflects all those ultrasound waves back to the transducer. It's going to create a shadow below it. Here's an example of really two large gallstones within the gallbladder on the right. And as we fan through that, you can see that they're very bright, and then they have these nice clean shadows below them. So all the ultrasound waves are bouncing off those stones, coming right back to the transducer, and everything below that seems black because there's no ultrasound waves beyond that. Now, gas scatter, that occurs whenever you are imaging something that has air within it. The most common thing that we image as air are the lungs and the bowel. So here in this image, we have a nice picture of the vertebral body here at the bottom, and then we see the aorta, IVC, just above the vertebral body, and then the liver. And this is a pretty nice image, but here we're starting to get a little bit of bowel gas. Do you see how that's ruining the image? It's scattering all of our ultrasound waves, and it gives us this sort of dirty shadow appearance where it creates a shadow. It's not as clean as that gallstone, like that gallstone created, but it creates a shadow nonetheless. And that's what scatter waves look like. Now, there are many other examples of artifacts, many examples of the artifacts we already covered, but I think we can better serve you by covering that in a separate lecture. So stay tuned for more and scan on.